Hey y'all, we are Memphis Community University and we are back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. And today what we're going to be talking about is we are going to be talking about the relationship between limits, continuity, and differentiability. And what we're going to see is that this concept is kind of difficult because we have to understand the theory behind these three words, at least at a basic level. But once we know the relationship between these words, we know what to look for, when we actually do these questions, they're actually going to be pretty easy. So these questions usually appear on the AP exam, both in the AB portion and the BC portion, in the multiple choice section, also sort of in the equivalent of college calculus exams. And you'll see that these questions are really easy. They just rely on a little bit of algebra and a little bit of calculus, but we do need to know what to do. So let's get started. I'm first going to talk about the definition of these three words: limits, continuity, and differentiability. And then as we talk about them, hopefully we can provide a nice little review or overview of these words because we've seen them before. And then we're going to be going into the questions, and then as we do the questions, if you know what to look for, again, they're not going to be too bad. So first off, let's talk about limits, which we've talked about before. So remember that there's really three kinds of limits. So the first two kinds of limits is approaching a number from the left or from the right. But the important thing about limits that you have to know is that it doesn't matter what's actually there at the limit, what the function value is. You're always just seeing what values you're approaching. So for example, if you have this point A and you have the point 1 and you have the point 2, let's say we have a function here and it's going towards this guy right here, and then on the right side it looks like this. So again, we don't actually care about whether this dot is closed or this dot is closed when we are doing limits, because we only care about what you're approaching. So for example, let's write out the two one-sided limits. In this case, it'd be the limit as x goes to a. When we do a left limit, that means approaching from the left. We put a superscript of minus. And then what is this number approaching? Well, if you approach this number, this is supposed to be the number 1. Maybe we'll make the dot a little bit bigger. But as you're going towards A from the left, notice the y value that you're approaching is going to be 1. So that's 1. What is the right value going to be? So that's written as limit as x goes to A with a plus function. Well, if you just travel along this function, it looks like a pretty nice function here, and you approach the number 1, notice the y value that you're approaching is 2. So this is going to be 2. Then if you actually wanted to find the function value, that's actually what's at the point A. The function value, the y value at A, that's the closed dot. In this case, it's f of A is equal to 1. But notice that this had no bearing on the limits. I could have put the closed dot on this one as well and switched it up. I could have had two open dots. It wouldn't have mattered. These two limits would have been the same because limits only care about what you're approaching and not what you're going towards. So let's see a full limit. So remember that if these two limits are equal, that means that you have an entire limit. We're going to be dealing with a lot of piecewise functions throughout this video, and sometimes the pieces sort of meet up, or at least are going towards the same thing on a collision course, if you will. So if you have a function here, you have your point A, you have this 1 and 2, hopefully I can draw them a little bit more to scale, and you have this function, you have this, and the function again is coming towards and from the left and the right when it's going towards A, towards the same point as opposed to two different points. This is going to be an open dot, and then we have a closed dot here. What we're going to do is we're trying to compute the limit in this case. Well, the limit is going to be the limit as x goes to A minus. Again, that's what you approach from the left. So as we're traveling along the function, which point are we going to? Notice that we're going to go to this y value 1, even if the y value actually isn't achieved at 1 at A. So this is going to be 1. Same thing for the right side. As we're traveling along, as we're just walking along this function, when we get towards the point A, as we get closer and closer to A, what y value are we approaching? Even if this dot is way up here, we're approaching the number 1. So this is going to be 1 as well. And when the two one-sided limits are equal to each other, that means that the entire limit as you're approaching A will be 1. And you're going along, and you're going towards the same number. So in this case, the limit as x goes to A of the function value is equal to 1. So what we're going to do throughout this video is we're going to try to compute the limits of a lot of piecewise functions. So what we need to do is we're going to need to compute two things. We need to compute the left limit and we need to compute the right limit. And then what we're going to do is hope, and we're going to hope that those two numbers are the same. So again, two separate things, and then that will, once we've proven that those two separate things are equal, the left limit and the right limit, that will mean that the limit exists and it's that number as well. Then what we're going to do is we're going to add the word continuous. The word continuous is you want this limit to actually be the function value. So you want this closed dot to be actually there. So that's what continuous means. In layman terms, at least for our purposes, it means that you don't lift up your pencil when you draw this graph. So if we close this dot, I wouldn't lift up my pencil as I drew it, or my marker, I guess. And so what we want to prove is that we want to prove that this is equal to the function value. So we're going to be dealing with a lot of three different processes, or three functions. No, I don't even know what I'm saying. Functions that have three parts. What we're going to show is that we're going to try to find left limits. We're going to try to find right limits. That'll be with the less than or greater than part of the piecewise function. And then for the equal part, that's going to help us prove continuity. But again, let me just recap this sort of with algebra without pictures. So let me erase this here. So again, what we're going to try to do is we're going to try to find the left limit of a function, because these are going to be pieces, so you have to do it in pieces. Then we're going to try to find the right limit. We're going to hope that they're the same, or prove that they're the same. If they're the same, that doesn't give us continuity just yet. It only tells us that the limit exists. So this is 3 and this is 3. That means that the limit of the function equals 3 as you approach the number a. But once we want to do that, we will probably want to try to prove continuity. So this is not sufficient, showing the left limit and the right limit. We do need to show that it's equal to a third thing, the function value. So this is f of a. This is continuous. Oh, only this equal is continuous. This equal, these two being equal, implies that this limit exists, and we do need to show it's an additional thing. So as we do these questions, what we're going to be doing a lot is showing three things are equal. The left limit is equal to the right limit, which makes this thing equal. This thing exists. And then we want to show that this new thing, the limit, equals the function value. So again, what we're going to be doing is showing that the left limit equals the right limit equals the function value, because these two things equaling the same. Sorry that I sort of erased my x a little bit. But these two being the same means that this is equal, or this exists, and we want to show that it's equal there. What you're going towards from the left is equal to what you're going towards for the right, so that means that you're going towards something, and what are you going towards something? We hope that it's the function value. And that's how it's going to work in these piecewise functions that involve the word continuous. We also need to talk about the word differentiable a little bit. So remember that differentiable sounds intimidating, but it's just related to derivatives. It's like the state of having a derivative. So a function is differentiable at x is equal to a number if the derivative exists there. Basically, the tangent line exists there, you can find the slope. And notice that if you have a function and that derivative exists at that point, that means that it will be continuous. Remember that there are limit definitions of the derivative. So the thing that I want you to know is that there's an implication, differentiability. Differentiability implies continuity, meaning that you won't lift your pencil because you need to be able to take a slope there. So implies continuity. But continuity does not imply differentiability, so it only works in this direction. So let's talk about ways that you can't be differentiable, because sometimes it's nice to look at counterexamples versus regular examples, and then you understand the question better, which is always nice. So what are 3 reasons that things can be not differentiable? These are the 3 main ways that appear on the AP exam. Well, the first one is not continuous. Again, if you lift up your pencil, you're not going to be able to find the slope there. If you're not continuous, well, differentiability implies continuity, so you can't be differentiable. The second one is going to be what is going to be called a sharp point. These look like absolute value. Absolute value is the prime example of this. So notice that if you have absolute value here, the derivative doesn't exist at this point, and it's because it's sharp. And why is being sharp relevant? Well, notice that the slope can't be this and this. There's two lines that are sharp, little V here. The slope can't be this guy and this guy, so that it can't be two things, so it's just neither of them. So this is another way that something is not differentiable. The third way is having a vertical tangent line. Meaning that, remember, tangent line is point and slope, where slope is derivative. So vertical tangent line means your slope is infinity, and that's why potentially you could be not differentiable, because your slope is infinity. What does that mean your derivative is? That means your derivative doesn't exist, so that means it's not differentiable because the derivative doesn't exist. So again, the things that I want you to know on this board here right now is that differentiability implies continuity, but not the other way around. You can be continuous, but not be differentiable. Really sharp points are our main examples of that. And there's three ways that are not differentiable for a function. They're not continuous, having a sharp point, or having a vertical tangent line at that point. But that's it, enough for theory. Let's talk about actual examples, and hopefully we can use that theory that we talked about for these examples. The main one is that when you're doing limits and when you're doing continuity, you want to find the left limit and the right limit, but that's not enough. You do need to verify that it's the third thing, so the function value. But let's first practice with one-sided limits on piecewise functions when the functions are listed. So a lot of our questions are going to look like this. We're going to have f of x, then we're going to have some sort of piecewise function, because those are the more interesting ones. Those are where problems might arise. We like challenges, of course. So in this case, we're going to have x squared plus 1. We're going to have 3x minus 2, something not too crazy. So remember, piecewise functions are functions that are pieces. Crazy, I know. You choose it. It's going to break up at a certain number. So I'm going to call this the split number. So basically, for x is smaller than 1, the function is this. For x is bigger than the 1, the function is this. And what we're going to try to do is we are going to try to find the two-sided limits. So let's try to find the limit as x goes to the split point 1 from the left, and then also from the right. So let's do that. So for the left, less than 1, or the left, remember you're approaching it from the left, so you're hitting numbers like 0.9, 0.99, 0.9999. Notice that all those numbers are less than 1, so you're going to be using this top function. The left goes with less than. So in this case, how do you compute this limit? Well, all you do is you plug in 1 into the function, but you just choose the appropriate function. Again, we're doing the top one because we're going from the left, and that's less than. So it's going to be 1 squared plus 1, so that's 2. Then, if we want to do the right one, well, these are the numbers bigger than 1 because you're starting off at 10, then going to 5, then going to 2, then going to 1.5, 1.01, 1.0001. You're approaching 1 from the right, so you're taking greater numbers and going towards 1. So in this case, we're going to choose the bottom function. Same thing, just plug it in as long as you know which one to plug in. Again, these questions are pretty easy. So in this case, it's going to be 3 times 1 minus 2, and that's going to be 3 minus 2, which is 1. So if you want to find the full limit, well, these two numbers did not match. So that means that the limit as x goes to 1 of f of x will equal does not exist. And what we're going to see is that there's going to be, most of the questions, these two numbers will match, and then we will want to prove continuous. So let's do that. So again, in these questions, when you have these piecewise functions, just choose the appropriate piece. Less than is left, right than is the greater one, because you're doing numbers greater than that piece, split point. And then in our next example, we'll see that we want to prove it as an additional thing. So let's erase this. So we have this. Let's change our function up a little bit to make it work. Let's do e to the x. Let's change this to zeros. And then we have e to the x plus, let's say, 2x. And then we're going to have something simple. Let's just have 1 plus x. So these are going to be my two functions here. So anytime you have piecewise functions, it might look like you have two pieces here, but you actually have three pieces. Notice that we have less than or equal to and greater than. So for this first piece is actually two pieces in one. They're just combining less than or equal to. So if you want, you can write this as three different pieces. You can erase the equal sign, and then you can just rewrite the top thing because it was less than or equal to. So we can rewrite it like this. and we can say, well, we're going to just break up this less than and equal to into two different properties. And now we're going to write it like this. Obviously, we can combine it like this, but I think it's better to write these three things out, or at least view them as three different pieces when we start doing these continuity questions. So the question is, find, or not find, show f of x is continuous at x is equal to 0. And what people do is they immediately just find the left limit or the right limit, but that unfortunately is not correct, because remember the definition of continuous is you don't just care about that the limit is going towards the same thing, that the function is going towards the same thing. You also want to make sure that that thing is actually there. So the limit equals the function value. So again, we need to find three different things, sort of four different things, but we're going to find the limit as x goes to a minus. In this case, it's going to be 0. We're going to find the limit as x goes to 0 plus by choosing the appropriate function, just like we did the previous one. And then what we're going to do is we're going to hope that these two things are equal, and then we have to ultimately find f of 1 as well. And f of 1 is going to be the same as the top one because we're using the same top piece, but I still need to at least write it out, because this is what continuous means. It doesn't mean that the limit exists, meaning it doesn't mean that just the left limit equals the right limit. You do need to find actually the f of 1, even if it's one of the same numbers, to verify that it is indeed continuous. So let's see how that works. So again, with these piecewise functions, you just want to use the correct piece. So as you're approaching 0, well, that's going to be the ones to the left of 0, meaning the ones less than 0. So it's going to be this piece right here. So it's going to be e to the 0 plus 2 times 0. Remember, e to the 0 is 1, so this is going to be 1. Then we need to do the limit from the x going from the right, or from the right, approaching 0. So what you do is you're going to plug in 0 into this guy, because remember, right goes with greater than. 0 plus 1, that's just going to be 1. And look at this. We have something great, because these two numbers are the same, but we can't stop here. These two numbers being the same just means that the limit as x goes to 1 of the function equals 1. If you want to prove continuous, remember continuous is this limit equals the function value. So even if the function value will be the same work as this top thing right here, because it's the same exact function, we do have to write it out. So what's f of 1? Instead of plugging in the less than or the greater than, we're going to plug it into the third one right here. So it's going to be, not f of 1, f of 0. Sorry about that. It's the limit of the, for some reason got confused with zeros. We're going towards the number 0 in this case, so we want to find f of 0. So again, for the left than, I don't even know what I'm saying anymore, but for the left one, we use the less than. For the greater one, we use the greater than. And for the actual function value, we're going to use the function value. So we're going to use the equal. So it's going to be e to the 0 plus 0, 2 times 0. That's going to be 1 plus 0, which is 1. So now we have actually proved continuous. So if you're writing a sentence down, again, you can't just say I found the left limit and the right limit and they were the same number. You have to refer to the words that the limit equals the function value. So because the limit of the function equals the function value, they're both equal to 1, that means that the function is continuous at 0. Continuous at x is equal to 0. So always three things. Left limit equals right limit, verify that they're same, and then that thing is the same as the actual function value for continuous. If you only do the first thing, you're only finding the limit. So now, these questions do appear on the free response questions showing them that a function is continuous. You'd be doing these steps. Left limit, right limit equals the limit equals the function value. Refer to both things, of course. These appear in the free response questions for A, B, but let's do the questions that appear on both portions of the exam, both the A, B, and the BC ones, when they're multiple choice questions. And what you're going to do is you're going to be solving for something. So let me erase this here. Let me erase this. Let's change the function up. So what we're going to do is we're going to be solving for a constant to make a certain function continuous at piecewise. So this is going to be, let's do ax plus 3. Let's do x squared minus 4a or something like this. And then we'll have x being 2 here. Let's put greater than or equal to 2 for x greater than 2. So these are the questions that really involve not much work. Basically what we're going to do is we're going to plug in 2 and then set them equal to each other. But I do want to talk about the precise way to write this. Precisely try to find the a. We're going to try to find the a such that f of x is continuous at x is equal to 2. So it's going to be the same thing, but when we do the left limit and the right limit, unlike our previous example, it's going to be in terms of a, and what we're going to do is we're going to make them equal to each other. So what is this question asking? Well, basically this is some function that looks like a line. This is a parabola, and at x equals 2, no matter, depending on what a is, these pieces are going to be sort of apart. And what we're going to do is we're going to try to find the a so that this piece matches with this parabola. So again, as you change a, this parabola is going to be shifting, this line is going to be shifting, so it's going to be something like this at the point 2, and we're going to find the a to make them match. And how we're going to do that is we're going to compute limits, because the definition of continuity, which is the most important thing about this video, is that the limit of the function as x approaches a equals f of a. So again, even if this thing looks like 2 different things, this is actually 3 different things. The less than, the greater than, or equal to. And we probably don't have to rewrite it, but we do want to view it as 3 different things. So what I need to do is I need to find 3 things. I need to find the limit as x goes to, the split point in this case is 2 for the function. Then I need to do it for the right. And then I need to find the function value. Because what I'm going to be hoping for is that the less than and the left and the right is going to be equal. That means the limit will exist, but that's not enough. That's not sufficient. You do need to check that it's equal to f of 2. So we have these 3 things. And again, these are 3 things, even if it looks like 2. For less than, we're going to use less. For to the right, we're going to use greater than. And for the function value, we're going to actually use the equal. So let's try to carry that plane out. For the left one, that means you're approaching x 2 from the left. We're going to be plugging it into this. So it looks like when we plug this in, we're obviously not plugging in for a. We're plugging in for x because we're solving for a. So it looks like we're going to get 2a plus 3. Again, I just plugged in x into the appropriate thing. The 2 into the x, we're doing less than. Then we are going to do greater than, approaching numbers from the right as we go towards 2. So that's going to be the numbers greater than 2, like 3, 2.5, 2.1, 2.01, and so on. So as we do that, we're going to plug in 2 into this function because this is the function that involves the greater than. So again, you're just choosing which function to plug it into. So we're going to plug in 2 into this. That's going to be 4 minus 4a. And then finally for the function value, because this piece involves the equal sign, what function are we going to choose? We're going to choose this bottom one. So again, we're going to get 4 minus 4a. And because there's really 2 pieces, even if we're viewing it as 3 pieces, there's going to be an equation where we're going to set all 3 of these things to be equal to each other. But notice that these bottom 2 are the same. So really, we're just going to set these 2 equal to each other. And why do we want these 2 equal to each other? Well, that means that the limit will exist and also the function value, because the function value happens to be one of the one-sided limits. So in this case, we're going to set 2a plus 3 to be equal to 4 minus 4a. And as I promised at the beginning of the video, all these equations are pretty simple. It's going to be 6a is equal to 1. I can't do math. Let's do that again. I think I did that right. Actually, this is minus 4, so we're going to bring it over. So it's 6a is equal to 1. That is actually correct. I can do something correct in my life. We're going to divide, and we're going to get a is equal to 1/6. So what is the significance of the answer here? This is the answer. Well, what this means is that this is the number that makes this function continuous. So if you graph 1/6x plus 3, and if you graph x squared minus 4 times 1/6, at x equals 2, you'll notice that they'll meet. It is going to be continuous. So let's write a little sentence here, even if this question doesn't require a sentence. So we're going to say if x is equal to, a is equal to 1/6, because the purpose of this sentence is to verify that we do know what continuous means. We didn't just find the one-sided limits, we actually found the limits and the function value. So because the limit as x goes to 2 of the function is equal to f of 2. If xa is equal to 1/6, that means the function is continuous at 2. And what is f of 2? What is the limit as f of 2? That's when you plug in 1/6 here, so it'd be 4 minus 4 times 1/6, or 2 times 1/6 plus 3. I believe that's 3 1/3. But again, what I'm trying to emphasize as much as possible is that in these questions, what you do is you just find these 3 things, but you need to find all 3 things, even if it seems like 2 of them will be the same, because that's what the definition requires. You need to show that these first 2 things are the same, and what you do is you force them to be the same by setting these 2 things to be equal, but still allude to that function value, because that's what continuous is. You're not just finding the limit, you're finding continuous. So if you want full credit, for example, in free response questions, you need to refer to both the function value and the limit value. But the actual work is pretty easy. You just plug into the appropriate function based off less than and left, greater than and right, or either function value and equal, and then you'll have a very, very easy algebra 1 equation, and you just solve that equation. So let's see a harder variant of this, where the givens are a little bit trickier. But if you talk about these questions in the way that I've outlined them before, doing the left limit, doing the right limit, finding the function value, you'll see that even these harder questions are really the same thing. So let me erase this. And let's change up the givens. So we're going to change up the givens. So in this case, my givens are going to be, instead of less than or equal to and then greater than, sometimes it's not equal to and equal. So when it's not equal to 2, what this function is going to be is it's going to be x squared minus 4, and then I need something that factors, so let's do x squared minus 3x. Well, if you plug in 2, you'll get 4 minus 6, so it looks like we need a plus 2 here. That seems right. So this is going to be my function value. So f of x will be this fraction when x is not equal to 2, but when x is equal to 2, it's just going to be the constant 2 times a. And again, what we're going to do is we're going to try to find a such that f of x is continuous at x equals 2, so the split point is x equals 2. So same thing as before, what we need to do is we need to find this limit right here. X goes to 2 from the left. We need to find the right limit. What we're going to do is, this is going to be in terms of some numbers or equation, and we're going to set it equal to the function value. So in these questions, you're going to always have 3 things, and you always set the 3 things to be equal to. It's going to be the creation of the question where 2 of the things will be equal to. Usually it's a limit and the function value, but as we'll see in this case, it's actually going to be the 2 limits that are equal to each other. But again, that doesn't matter. Just always form these 3 things and set them equal to each other, even if all of them, 2 of them are already equal to each other, if that makes sense. So if you look at this, again, it's not broken up as less than and equal to and greater than, or less than and greater than or equal to. It's actually broken up into not equal and equal. But this is actually 3 things as well. Even if it looks like it's this and this, what does not equal mean in the context of less than or greater than? Well, that means that you're either less than or greater than that number. If you're not equal to 2, you're either less than 2 or you're greater than 2. So when we're choosing what function to plug this in, this is the same thing as less than or greater than. So let's get started. Same thing as before. What we need to do is we are going to find the limit of the f of x as x approaches 2 from the left and as x approaches 2 from the right. But we're going to be using this top function because that's the function that involves less than or greater than, even if it was presented as not equal, because they're the same thing. So when we plug in this 2, looks like we're going to get the limit as x goes to 2 minus of this top thing right here. It's going to be 2x squared minus 3x plus 2 over x squared minus 4. When you plug in 2, notice that something weird happens. You're going to get 4 minus 6 plus 2, that's 0. You get 0 over 0. So there's multiple ways to do this limit. You can factor everything and cancel out the top. That's really the pre-calculus way. But we just learned L'Hopital's rule, so I'm going to do L'Hopital's rule. To take the L'Hopital's rule, you take the derivative of the top and the bottom. So that's going to be 2x minus 3. And that's going to just be 2x. Then I'm going to plug in 2. When you plug in 2, it's going to be 4 minus 3, which is 1, over 2. So it's going to be 1/4. And this is what the left limit is. Again, how do we choose this function? Usually it'll have the character less than, But we notice that for less than, it does go with less than, and less than is part of not equal. So that's why we chose to plug it into this way. The limit wasn't as easy as the limits from the past. It wasn't just plug in because we did get an indeterminate form. So what we did is we did L'Hopital's rule. So now what we're going to do is the right limit. The right limit again is that top function here. So again, the top function is pairing the left and the right. And what we're going to do is we're going to plug it in here. It's going to be the same exact limit. So 2 plus f of x. We're still going to get 1/4 because it'll be all of this work. I rewrite the same thing, so let's rewrite that function. 1/4. So we're going to put 1/4 and 1/4, but notice that 1/4 is not the answer. 1/4 is not the a that we want. 1/4 is just the limit of this function. So we do need to set the limit of the function to be equal to the function value. This is where this is incorporated. What is the function value? It's 2a. So what's the answer? Well, it's going to be 2a is equal to 1/4. We're going to bring the a over, bring the 4 over, cross multiply. So it seems like the a is going to be just 1/8. Because 2 times 1/4 is 1/8 is 1/4. And this is our answer. So again, the answer isn't this 1/4. That's what some students think. That is actually just the limit. You're always setting 3 things to be equal to. The left limit, the right limit, to make sure that the limit exists, and you want to make it equal to the function value. So you're setting all those to equal to each other and solving. In the previous question, what we did is we had the less than and the function value equaling, I think, the greater than. But in this one, the left one and the right one are already equal, and we're just setting it equal to the function value. Again, you're always setting these 3 things to be equal to each other, and the one that you might forget is the function value itself. But in order for continuous to exist, the limit equals in the function value. And that's how this works. So again, I keep saying the word again and again and again and again, but I'm trying to reiterate this as much as possible. Continuous is when the function equals the limit, and you're going to just set this up every single time. The left limit, the right limit, and the function value determine what you need to plug in. You look at the functions, and if you're going from the left, you plug it into the less than. If you're going from the right, you're plugging in the greater than, even if it's presented as not equal. And then for the function value, you plug it in equal. You get 2 things that look the exact same out of the 3, but you're going to set all 3 things to be equal to and solve. Finally, let's do the hardest variation of the questions, where instead of continuous, we have differentiable. So remember, the key is that differentiability implies continuity, which is why these questions will involve 2 variables. What we're going to do is we're going to do the same exact thing, except we're going to have to do it twice. One for the function and one for the derivative as a piecewise function in order for those derivatives to exist. So in this case, we're going to find a and b such that f is differentiable at let's say x is equal to -1. So my function is going to be, let's say ax squared plus b for x smaller than 1, -1. And then for our bottom function, let's do 3bx minus 4x. Hopefully this will work out. I'm just looking at the question. I really want this to work out. I believe it will, so let's just get going. It would be very unfortunate if this did not work out. Let's not do equal for this one. So the word changed from continuous to differentiable. And the word changing, remember that differentiable is a little bit more complicated. It's more specific. Differentiability implies continuity, not the other way around. But all functions that are differentiable are continuous. So the first thing in these questions is to do the same thing that we did in the previous ones. You need to set up continuous. But because all that work required a lot of just writing, remember that for our continuouses, we'll just find the left limit and the right limit and the function value. The left limit would be this function right here. The right limit would be this function right here because it's greater than. And then the function value, because of this equal, would be this one right here. So we would be setting these 2 things to be equal, and then we would plug in -1 because that's how we computed the limits. But we're not going to write all that stuff out. We're just going to skip to that step. What we're going to do is we're going to take these 2 guys, set them equal, and plug in -1. So when we do that, we get a times -1 squared plus b equals 3b times negative 1. Let's put the work a little bit over to the side here so we have enough space. So again, all I'm doing is I'm setting these two things equal to each other and plugging in negative 1. So it's a times negative 1 squared plus b equals 3 times b times negative 1 minus 4 times negative 1. So I'm just going to simplify this a little bit. It looks like it's going to be a plus b, because the negative 1 squared is 1, of course. Then you're going to get minus 3b plus 4. And then we're going to solve this a little bit more. A plus 2b equals 4. So I'm going to box this. This is not my answer, but notice that we have two variables in these questions. And how do you solve something with two variables? Well, we're going to use a system of equations. So this is just one of our equations. This comes from just plugging in and setting equal. Then what you do is you just do the same thing, but with the derivative. The derivative is a little bit tricky, so I'm going to take it slowly. The derivative of ax squared is just going to be 2ax. That comes from the power rule. But the derivative of plus b, while it looks like it's plus 1, because the derivative of x is 1, keep in mind that in these questions, the a's and the b's will eventually be constants. So the derivative of plus b actually is 0. So this is actually the derivative of the top piece. And the derivative of the bottom piece is going to be 3b minus 4. So now, because the derivative of like 5x is 5, so the derivative of 3bx is just 3b, and the derivative of minus 4x isn't that bad, it's just minus 4. So then you do the same thing. So in the first one, what we did is we plugged in negative 1 into both of them and set them equal. And we're going to do the same thing in here. We're going to plug in negative 1 into both of these and set them equal. So it's going to be minus 2a, because it's going to be, we can write that some more steps if you want. 2a times negative 1 equals 3b minus 4. So, because we plugged in negative 1 for this x. So it looks like it's minus 2a equals 3b minus 4. So then what you do is you just solve this system of equations. You can use any way you want. You can use elimination, you can use substitution. The best way in this case might be substitution here. So let's solve for this. A is equal to 4 minus 2b. Let's plug this n into this a. So it looks like we have minus 2 times 4 minus 2b. This question is very involved, but we're almost done. We get 3b minus 4, and then let's go up. Even that's not how you do math. You should go down, but we sort of ran out of space here. It's going to be minus 8 plus 4b is equal to 3b minus 4. So we are almost done. What is this b? Let's see if we can do the question right. Hopefully I've been solving this right. You'll let me know in the comments. But notice that it will just be b is equal to, you add 8 to both equations, so it's going to be b is equal to 4. Definitely not going to complain about that. Then you do need to find a. A is equal to 4 minus 2b, so it looks like it's going to be 4 minus 8, so a is going to be negative 4, so that's going to be our answer. So let's box it here. So a is going to be negative 4, b is going to be 4. That seems like it's going to be right, because negative 4 plus 8 is 4, and then what was our second equation? This guy right here. 3 times 4 is 12. 12 minus 4 is 8. Negative 2 times negative 4 is 8. So it looks like we have the right thing. I'm assuming that this is right. But this work has been very convoluted. So let's talk about what we did. Let's recap this, and then we will be good to go. So again, when you have a and b, when you have the word differentiable, the question becomes a lot harder. You just have to do the continuous ones twice. So what you do is you first take your number, your split point, you plug it in, and you set your plug it into x, set these equations equal. That's what we did here. And then we sort of box this guy because this is one of the equations. Then we took the derivative, and we're going to do the same thing with the derivative. Keep in mind that the derivative of constants is still 0. B is a constant, so that's why this derivative is this. And then the derivative of 3bx is 3b. The derivative of minus 4x is minus 4. Then we took these two pieces of the derivative and plugged in negative 1 again. Set them equal. And now we have this equation. Once we have these two equations, you just solve these two equations however you need. We did substitution. We ended up getting that a is equal to minus 4 and b is equal to 4. And that was the answer. So what is the significance of these numbers? First off, if you plug in negative 4 for b and for a, then you plugged in negative 1, you would show that this function is continuous because differentiability implies continuity, so you need continuity. Then also the derivative would work out as well. If you plugged in -4 and 4 for A and B, plugged in -1, you would have these two numbers being consistent, and that's what you want so that you can have slope there. So this has been a very long video, probably didn't explain things incredible. Basically, for these piecewise functions, if you're doing the word continuous, well, what does the word continuous mean? That means the limit equals the function value. So what you need to do is you need to find the left limit and the right limit to make sure that the limit exists, but then find that function value. And how do you find all of these things? Well, you just choose the appropriate piece of the function to plug it into. Differentiability is the same thing. For continuity, you just plug in and set equal. For differentiability, you just have to do it twice after taking the derivative. As you can imagine, you might want more practice examples for this. So like normal, we do have a Girls Teach Calculus video in the description below, where one of my former students practices several of these questions. She proves that functions are continuous. She finds one-sided limits. She does these piecewise function questions where you find a certain constant to make a function continuous, where you find a pair of constants to make a function differentiable. So if you want more practice with that, go check out that video. Thanks again for watching. Hopefully this wasn't the worst explanation of this that is imaginable, but it's not actually that bad. If you get past the theory, just set things equal to each other, plug it in. As long as you know what to set equal to each other, you should be good to go. Thanks again for watching, just like normal, and hopefully I will see you next time as we continue more derivative topics or topics that involve derivatives. Thanks again for watching.